Good morning, friends. After the discussion of de Broglie's wavelength, lambda is equal to h upon p, where the lambda is equal to h upon nv, that equation represents the dual nature of matter. The lambda is associated with the wave nature of matter, and p, that means the momentum, associated with particle nature of a matter. Right? That means the both nature of matter does not exist at the same time. That means we can't measure simultaneously at the same time the both nature of the matter. For that purpose here, the Heisenberg's uncertainty principle. Today we are going to discuss about the Heisenberg's uncertainty principle and also the wave packet and first two numerical of illustration. Okay, now the question is that explain Heisenberg's uncertainty principle. So the answer is position of particle, that means the electron or the other, and momentum cannot be measured simultaneously at a time. Because as we consider the particle nature, so its momentum is fixed. That means the particle nature the momentum is represent the particle nature and wavelength represent the wave nature of a matter. If the particle nature is fixed, at that time its position is fixed. But in wave nature, as we consider the matter as a wave, so its position is not fixed. Okay, here we are going to discuss on the basis of the Heisenberg's principle. Position of particle and momentum cannot be measured simultaneously at the same time. There is always uncertainty in position delta x and in momentum is delta p. So Heisenberg suggested the equation delta x into delta p is approximately h cut. That is read as h cut. Now the value of h cut is h upon 2 pi. H is the Planck's constant and its value is 6.626 into 10 is to minus 34 joule into second. Already we discussed earlier. Now delta x into delta p is equal to h cut. Therefore delta x into delta p is equal to h upon 2 pi. Here I substitute the value of h cut as h upon 2 pi. So this equation. From equation 1, if delta x is equal to 0, that means the uncertainty in position is 0, that means the position of the particle is fixed. At that time, delta p becomes the infinite. As we take the delta x is equal to 0, so this term is 0. That means delta x is in this side, delta x is 0, therefore delta p is infinite. That means the change in momentum becomes the infinite, and when delta p, that means the change in momentum is infinite, then delta x becomes the infinite. Again, so that's the uncertainty in position is delta x and uncertainty in momentum is delta p. Therefore, delta x into delta p approximately h cut. Already you learned in chemistry this principle of Heisenberg. Therefore, delta x into delta p is equal to h upon 2 pi. Here we substitute the h cut as h upon 2 pi. So this equation, if delta x tends to 0, at that time the delta p becomes the more and more infinite. That means the uncertain. As we make the position of particle certain, at that time the momentum of the particle becomes the more uncertain. Now the same is when the delta p tends to 0, that means the momentum of the particle or the matter is fixed. That means the certain, at that time its position becomes the more uncertain. By making the one quantity definite, another quantity becomes the undefinite. This is the reality of microscopic particle. So according to the Heisenberg suggested that as we make the one physical quantity more definite, so other quantity becomes more undefinite. If the electron possesses the definite momentum p, so the change in momentum is 0, then it has the definite wavelength lambda. according to this equation, that means the de Broglie's wavelength lambda is equal to h upon p. So a wave of definite wavelength extends over space. So we know that the wave is like this manner. So wave of definite wavelength extended in all over space, thus the electron is not localized at a particular point in any finite region of the space. Therefore its position becomes the more undefinite. Right? And that is its position uncertainty is infinite. That means the delta x tends to infinite, which is consist with uncertainty principle. Again, by making the one quantity definite, that means the delta x is fixed, that means the position is fixed, therefore delta x tends to 0, so its momentum becomes the more undefinite. Quantity becomes the undefinite. This is reality of microscopic particle. Now, if the electron possesses the definite momentum p, therefore the change in momentum is 0, then it has the definite wavelength according to the de Broglie's wavelength equation. Therefore lambda is equal to h upon p. P is fixed, therefore lambda is also fixed. So here we consider the matter as a wave. A wave of the definite wavelength extends over the space like this. Therefore the position of a particle nature is more uncertain. Therefore the electron is not localized in any finite region of the space. So that is its position uncertainty is infinite. Because the p is fixed, that means the delta p tends to 0, so delta x tends to infinite. So which is consistent with uncertainty principle. Clear? Okay. Now we start our discussion about the wave packet. Okay, now next question is that what is the wave packet and explained by using the necessary diagram. Already we discussed about the Heisenberg's uncertainty principle. So delta x uncertainty in position and delta p is uncertainty in momentum. So how we make the certain both at a time? Actually that is not possible. So for that purpose we are using the concept of the wave packet. Wave packet is resultant wave obtained by superposition of waves of different wavelengths. What is the wave packet? The resultant wave obtained by superposition of waves of different wavelengths is known as the wave packet. That means in wave packet there is the bundle of numbers of the wave. If the more than one waves or the two waves are superposed on each other, at that time, whatever the resultant packet is obtained, that is known as the wave packet. Again, the resultant wave obtained by superposition of waves of different wavelengths is known as the wave packet. Now, the matter wave, that means the single wave associated with electron, is not extended in infinite space. It is a wave packet extended about a central wavelength. Now there is a figure of the wave packet because here the numbers of the waves with different wavelengths are superposed. Therefore, this type of the figure is obtained. So it is a wave packet extended about a central wavelength. Here the central wavelength is this. Now the other waves are around the central wavelength. In this condition, delta x is not infinite, but it has the some definite value, and this depends on range of wave packet. Now, if we consider the wave packet, that means due to the superposition of the wave, so amplitude of the wave is now becomes the fixed. Therefore, the position of a particle becomes the definite value, and which depends on the range of wave packet. Earlier we discussed in Heisenberg's uncertainty principle. If the wavelength and momentum are fixed, therefore the position of electron or the particle becomes the more uncertain. To make the position uncertain by considering the wave nature, we take the numbers of the waves superposed on each other. That means the concept of the wave packet. In this condition, that means in wave packet, the delta x is not infinite, but it has some definite value, and which depends on the range of wave packet. Also, the wave packet does not have the definite wavelength, but made up of numbers of the wavelengths about the central wavelength. Actually, the wave packet has no definite wavelength. Wave packet is made up of numbers of the superposition of the waves with the different wavelength. But the wave packet has the central wavelength. The description of wave packet with the de Broglie relation and Bohr's probability interpretation reproduce the Heisenberg's uncertainty principle exactly. So here the figure A shows the schematic diagram of wave packet, and figure B shows the extended wavelength wave with fixed wavelength. There is the wave with fixed wavelength, and that is the schematic diagram of the wave packet. Here the bunch of the wavelength are present in this wave. Okay. Now the wave packet description or the describe of an electron is corresponding to the spread of wavelength around some central wavelength. It is associated with an uncertainty in position delta x and in momentum. So here the figure A represents the wave packet. The description of an electron is corresponding to a spread of wavelength and the some central wavelength. It is associated with an uncertainty in position delta x and uncertainty in momentum delta p. Now, the matter wave corresponding to a definite momentum of electron extended all over the space. So here, there is a matter wave with a single wavelength. Here, the lambda is fixed. So according to the equation, lambda is equal to h upon p. Momentum is also definite value. Therefore, delta p tends to 0. So delta p is equal to 0, but the position of the particle or the electron in this wave becomes the more infinite. So in short, the wave packet is the concept of the resultant wave obtained by superposition of waves with definite wavelength. By considering the concept of the wave packet, we make the position of the particle considering as a wave quite fixed. But momentum is uncertain because the wave packet is the bundle of the wavelength. Therefore, wavelength is not fixed. Therefore, we not obtain the particular value of momentum because the wavelength is not fixed. Clear this? So that is the concept of the wave packet and Heisenberg's uncertainty principle. While in case of the single wave with a definite wavelength, momentum is fixed, therefore change in momentum is 0, but the position becomes the more uncertain. Clear? So that is the concept of wave packet. Okay, now we discussing about some numerical of illustration. The first numerical is given because already we discussed about the Einstein's explanation and also the de Broglie's wavelength and also the properties of characteristic of photon. So here the equation in this chapter are very less, only 4-5 equations. One is the maximum kinetic energy is equal to hf minus phi 0, or the EV0 is equal to hf minus phi 0, and energy of the photon hf, momentum of photon hf upon c, or the h upon lambda, or the lambda is equal to h upon p, and also de Broglie's wavelength, lambda is equal to h upon p. Right? So on the base of this we take the first some numerical, and after we discuss that the Davison and Germer's experiment. Now the first illustration is the monochromatic light of the frequency 6 into 10 is to 14 hertz is produced by a laser beam. The power emitted is 2 into 10 is to minus 3 watt. So what is the energy of the photon in light beam? And second part is how many photons per second on an average are emitted by the source. For that purpose, first what is given? Frequency F is given is 6 into 10 is to 14 hertz. And the power emitted is given 2 into 10 is to minus 3 watt. Planck's constant H is equal to 6.63 into 10 is to minus 34 joule into second. Keep in mind the value of Planck's constant. Sometime in exam that is not given. So you have to keep in mind the value of Planck's constant. First we need to find out, so what is the energy of photon in a light? So first part is energy of photon. Energy of each photon. From characteristic of photon, energy of photon E is equal to hf. Frequency is given. H is the Planck's constant, so its value is 6.63 into 10 is to minus 34 into frequency is 6 into 10 is to 40. Therefore, the simplification is 39.78 into 10 is to minus 20 joule. So that can be also written as 3.98 into 10 is to minus 19 joule. That is the energy of every photon in a beam of light. Now in part B, what we have to find out how many numbers of the photon per second on an average are emitted by the source. That means we have to find out the number of the photon emitted by the source per second. So we know that the power is given. Power is the total energy emitted by the source in unit time. Power P is equal to total energy upon time. Okay. Here we find out the energy of the one photon. We assume that suppose there are capital N number of the photon are emitted per second. Therefore power P is equal to N into energy of one photon. Second B. If N photons are emitted, N numbers of the photon, per second by the source. Therefore, power P is equal to number of photon into energy of one photon. Energy of one photon is equal to N into E. Therefore, number of photon emitted is equal to P upon. Here the power is given 2 into 10 is to minus 3. 2 into 10 is to minus 3, and energy of one photon already we obtained 3.98 into 10 is to minus 90. 10 is to minus 90. Now calculate yourself. So we obtain the 5 into 10 is to 15 photons per second. So this number of the photons are emitted on an average per second by the source. So where is the numerical here? Only we need to apply the equation. Okay. Now on the base of this numerical, sometimes the numerical value are changed. Wording are given the same for homework. So here instead of the 6 into 10 is to 14. Suppose the value are given like this way. The 5 into 10 is to 14. 5 into 10 is to 14 hertz. And the power emitted is, instead of the 2 into 10 is to minus 3 watt, suppose the 66 watt. 66 watt. Find the number of photons emitted by the source per second. So you have to calculate yourself. The answer is 2 into 10 is to 22 photons per second. Very. Now the next illustration, the work function of cesium is given 2.14 electron volt. Now listen here. The work function, that means the minimum energy required to produce the photoelectron from the photosensitive surface. That means the energy. Unit of energy is in electron volt. Generally, in numerical, we are using the energy in joule. So we have to convert first the work function into joule. Therefore, work function I is equal to 2.14 electron volt. So how we convert into the electron volt into joule? So we have to multiply by the charge of an electron. Therefore, 2.14 into 1.6 into 10 is to minus 19 joule. Right? Therefore, we obtain the work function is 3.424 into 10 is to minus 19 joule. Minus 19. First, we have to find out the threshold frequency. First, we have to find out the threshold frequency. The wavelength of the incident light, then we have to also find out the wavelength of incident light if photoelectric current brought to zero by stopping potential of 0.60 volt. Right? Planck's constant is 6.63. Here the stopping potential is given V0 is equal to 0.60 volt. Work function phi 0 is given as, what is the value? 2.14 electron volt. 2.14 electron. So first, the threshold frequency. So we know that the work function phi 0 is equal to HF0. Therefore, F0 is equal to phi 0 upon H. Phi 0 upon H. Already we obtained the phi 0 in joule. So 3.424 into 10 is to minus 19. And Planck's constant is 6.63 into 10 is to minus 34. So we obtain the frequency of the threshold frequency is 5.16 into 10 is to 14 hertz. That is the value of threshold frequency. Now B part. We have to find out the wavelength of the incident light. If the photoelectric current is brought to zero by the stopping potential is 0.60 volt. So from photoelectric equation, from photoelectric equation, we know that EV0 is equal to HF minus phi 0. HF minus phi 0. Here are two methods. Find out the F and convert the C is equal to F lambda. Right? Or the second method is that EV0 plus phi 0 is equal to HF. Right? But we know that C is equal to F lambda. Therefore, F is equal to C upon lambda. Substitute here. So it's equal to HC upon lambda is equal to EV0 plus phi 0. Okay. Therefore, lambda is equal to hc upon EV0 plus phi 0. Here we have to substitute the value of h 6.63 into 10 is to minus 34 into c 3 into 10 is to 8 upon e 1.6 into 10 is to minus 19. V0 is given 0.60 plus phi 0 already we obtained in Joule 3.41424 into 10 is to minus 19. In this simplified we obtain the value of wavelength is 454 into 10 is to minus 9 meter. Actually there is the 454 nanometer. So that is the wavelength. Again, in second illustration, wave function is given and also the stopping potential is given. First, we have to find out the threshold frequency. Threshold frequency is the minimum frequency required to produce the photoelectric effect. Therefore, phi 0 is equal to hf0. Using this concept, f0 is equal to phi 0 upon h. Phi 0 already given in electron volt, we have to convert into joule by this method, multiplying the given value of electron volt with 1.6 into 10 is to minus 19. Therefore, 3.424 into 10 is to minus 19 joule we obtain. Thus, we obtain the threshold frequency. Now, we also require the wavelength of incident light. If the photoelectric current is brought to 0 by the stopping potential 0.60. So from photoelectric equation EV0 is equal to hf minus phi 0. Phi 0 already known, h given, EV0 already known. So by using this equation we can calculate it. Sometimes the numerical is also asked by changing the value. So here the wave function is 2.14. For homework, suppose the wave function is given 2.3 electron volt. 2.3 electron volt. And stopping potential is given as the same value 0.60 volt. Instead of the system, here the potassium is given K. Find the same physical quantity. So here the in answer F0 is obtained. F0 is obtained 5.55 into 10 is to 14 Hertz. And wavelength is obtained 429 nanometer. That is the answer of extra question. Only if instead of the 2.14 electron volt, we make the wave function is 2.3 electron volt. What are the change occurs in wavelength of incident light and threshold frequency? Right?